For this slide, we shall start our discussion on vibrations. So we can see the single potential energy surface with a minimum at some point R naught, and we shall expand our potential energy of the system, being a molecule or crystal, in terms of in a Taylor series with respect to atomic displacements. So this quantities ui corresponds to displacements of atomic positions from the corresponding equilibrium positions, and the index I or J, they represent degrees of freedom, which are comprised of two indices. One is capital A is atomic index, atom number, and alpha is the direction of the displacements x, y, z. So the linear term in this expansion disappears because we expand around the positions at equilibrium, as was already mentioned. So the first non-zero term is quadratic in atomic displacements, and this is called harmonic approximation. The coefficient to this harmonic term, this phi ij, they form a matrix which is called force constant matrix. This matrix is symmetric because it corresponds to the second derivatives of the energy with respect to atomic displacements, and these second derivatives are symmetric. The force constant matrix has some properties which we shall discuss now. The first property is general for any system, including periodic systems and molecules, non-periodic systems. And it goes as follows. So this force constant matrix, when written explicitly via atoms and displacements, it forms this kind of matrix. So the first property states that if you sum all elements of that matrix with respect to an atom index A alpha, A prime, you will get 0. And this follows from the following consideration. Imagine we will displace all atoms by the same vector V. In that case, the energy would not change, of course, because the whole crystal will be just translated by that vector. And the atomic forces, if you calculate them from this expression for the energy, they would simply be the derivative of the energy with respect to displacement. And if you differentiate this form, quadratic form, you will get this linear term. So that force should be equal to 0 for any atom. On the other hand, if all the displacements are the same and equal to V, you can take them out of the sum and you arrive at that expression. And because the displacement can be arbitrary, that sum here should be 0. This is what our first property is. The second property is related specifically to periodic crystals. In the case of periodic crystals, atomic index capital A should be written more precisely because we have atoms, we have to indicate atoms both in the unit cell they belong to, and this corresponds, we have to specifically indicate the particular lattice vector, and also we have to indicate within this cell what this atom is, so we have to indicate the basis index S. So to indicate atoms, to indicate degrees of freedom in a periodic crystal, you have to indicate these three letters. One, L, is the lattice vector, S is the basis in the unit cell, and alpha is the Cartesian component x, y, z. So let's remember this, and as a result of that, the force constant matrix Fij would have this form. So you have to have a left index as L S alpha and the right index as L prime S prime alpha prime. So what we're going to prove now is that for periodic crystal, this force constant matrix will not depend just on the L and L prime separately, but will only depend on their difference. And this is a consequence of the periodic symmetry. So in order to prove that, let's imagine that I displace one atom in the cell L type S in the direction alpha by some amount. All other displacement will be zero. The total energy change would be given by this term, but if all u's are zero apart from this one, the change of the energy would be described by that expression. So in which you will have this diagonal element of the force constant matrix. The point is that that diagonal element would not depend on L, because if it would, that change of energy would be different if you displace exactly the same atom in exactly the same direction by the same exactly the same amount in a different cell, which is, of course, is not possible due to periodic symmetry. It doesn't really matter from which cell you will displace a single atom. So therefore, this element would not depend on L. Now we will make another experiment. We'll displace two atoms by different amounts. But they will be in different cell. One atom would be in the cell L, another atom would be in the cell L prime. All other displacement will be zero. So only two displacements for 2 degrees of freedom are non-zero in this case. From this sum, we will have only 3 non-zero terms then. We know that these two coefficients don't depend on the L and L prime respectively. So only this coefficient still may depend on this indices L and L prime. However, it is clear that that energy difference which we created by displacing these two atoms may only depend on the relative positions of these two atoms, so on the difference of these two lattice vectors L and L prime. Therefore, as these two coefficients do not depend on the vectors L and L prime at all, so this coefficient should depend on their difference. So we proved that the force constant matrix for a periodic system may only depend on the difference of the lattice vectors L and L prime. And in fact, that property doesn't contradict the first property we just discovered, that if L and L prime the same, the difference is zero. So the matrix element, the element of this matrix does not depend on the L of the lattice vector. Now let's discuss how shall we solve classically. The quantum treatment will be considered later. How shall we solve classically the vibrations of a system of many atoms in the harmonic approximation? Our first discussion will be general, applicable to any type of system, periodic or not. But then we will consider specifically a periodic system. So our consideration will be based on the Hamiltonian of the whole system, which is basically the total energy, which consists of the kinetic energy and the potential energy of our atoms in the harmonic approximation. And again, indices ij, for the simplicity of notations, are corresponding here to the degrees of freedom. So Newtonian equations of motion are constructed by simply saying that the time derivative of the momentum p, which is the mass time velocity, is equal to the force. As force on the degree of acting on the degree of freedom k is obtained by taking minus derivative of the potential energy with respect to atomic displacement, and that derivative is easily calculated and is given here. So our Newtonian equations of motion are here, and we have many such equations, second order differential equations, for each degree of freedom of our system. And these equations can be written in a matrix form like this. If we collect all the coefficients of the force constant matrix into the force constant matrix F, we collect all our displacements in the vector u, and we collect all our masses, put them along the diagonal into the square matrix of the mass m. It will be convenient to introduce also square root of the mass and 1 over square root of the mass, and these are obtained by simply placing along the diagonal either square roots of the masses, atomic masses, or 1 over square roots, these atomic masses, for the m in the power 1/2 or at the power minus 1/2. And that little notational convenience allows us to reformulate this equation and construct it in a more appropriate form. So first of all, we shall introduce, instead of the vector of atomic displacement, a massless vector of displacement v. So v is written simply as a matrix product of the square root of the matrix M and U. Correspondingly, U, this we will need later on, is M minus 1/2 V. Yeah, let's remember this result. We will need this later on. Okay. Then we replace U from here into our equations, and we will obtain this this equation here. Then we multiply both sides of this equation by m in the power minus half. So that m would then disappear, and this m minus half will reappear here. So if we, in the right hand side, so if we introduce a matrix D, which is written like this, which is called dynamical matrix, you see it's formed from the force constant matrix, which is multiplied from the left and from the right by m minus 1/2, which makes this matrix also symmetric. So if we introduce this dynamical matrix, our equations of motion would eventually be written like this for the massless displacements v vector. And if you consider a scalar variant of this, so imagine we have just a single degree of freedom, then the equation would basically be an equation of a harmonic oscillator. So this is what we expect. We expect that these solutions of this equation v as functions of time would oscillate. And that would guide us to finding a simple solution of this equation. So what we need to do is to write this vector as a product of a trial vector y, which is a constant vector, an exponential function with a frequency omega. That exponential ansatz ensures that our solution v would be an oscillating solution. This is what we expect from solving these vibrational equations. So if we take this ansatz and substitute it in here, we would arrive at this equation after cancelling out on the exponential function of time. So you see, this equation doesn't contain time anymore, and therefore our guess for the solution was actually correct. This equation we obtained can be rewritten in that form, which should look familiar, because what it is actually is the eigenvalue eigenvector problem for the square matrix, symmetric matrix D. So the vector y we need to find, which appears here, is an eigenvector, and omega square, which we also need because it appears in our trial ansatz for v of time, v is a function of time, is an eigenvalue. So omega square is an eigenvalue, y is an eigenvector. And as you know from mathematics, from linear algebra, we have as many eigenvectors, pairs of eigenvectors and eigenvalues as the dimension of the matrix D. So for each eigenvalue, eigenvector, we will distinguish with the index lambda. So we have y lambda for the eigenvector and omega square lambda for the eigenvalue. Because u, our actual vector of displacements, is related to v like this, and v is written like that, we can write for each solution lambda of this eigenproblem, we can write the following expression for the atomic displacement. So this will be specific atomic displacement. So all atoms will oscillate because of this exponential factor with a frequency omega lambda, and with the amplitudes related to this this product of m minus 1/2 and y lambda for this particular solution lambda of this eigenproblem. And these are called normal modes. So we'll have as many normal modes in our system as is dimensionality of our system, as is the dimensionality of the dynamical matrix. Okay, so we know how to solve this eigenvector eigenvalue problem. We'll start from setting the determinant of it to 0, and this would give us all squares of the frequencies. And by the way, these squares of the frequencies are bound to be real because the matrix D is symmetric, and therefore we know from mathematics that all eigenvalues of the symmetric matrix are real. In fact, the matrix D is also real itself, and therefore its eigenvectors can always be chosen as real. But because we have this exponential ansatz, we actually uh, can choose this product as real. So in other words, this real displacement will be a collection of cos and sine functions with the same frequency omega lambda in the end. Eigenvectors of any symmetric matrix can be chosen to be orthonormal, so it will be orthogonal. So different with different lambda and lambda prime, the dot product here will be 0, and for the same lambda and lambda prime, the dot product will be equal to 1. They also satisfy so-called completeness relationship, um, and this comes from the fact that if you place eigenvectors as columns, the matrix you construct this way, which is called a model matrix of matrix D, and it will be orthogonal because its columns form a set of orthonormal vectors. But by the same token, the rows of the same matrix will also be orthogonal and normalized to 1. And therefore, if you write this condition in this way, remember, each column corresponds to a new lambda, you will arrive at that condition of the completeness. So this is just a consequence of the fact that the model matrix is orthogonal matrix.